Looking at an empty parcel of land, it is easy to see a blank page waiting for a foundation. A developer views this raw terrain as a highly constrained geographic node. This site analysis board maps the physical, environmental, and legal realities of a plot. Generating it requires site selection, a rigorous, multivariable evaluation, testing a geographic location against development requirements to determine if construction is viable. A plot of land is never truly empty. It is governed by an invisible matrix of physical laws, legal zoning boundaries, and local community dynamics. All of these factors have to be decoded before a single shovel hits the earth. Constructing a building that withstands the local climate and survives the legal system requires coordinating several conflicting technical fields at once. The Site Analysis Board is the ultimate visual output of that coordination. It proves, on paper, that a site works. We are going to reverse engineer this board. By breaking down its components, we can isolate exactly why each piece of environmental and legal data is gathered and who is responsible for acquiring it. Mastering this analytical framework is the difference between blindly following a municipal checklist and executing strategic, risk-mitigating development. This diagram illustrates the screening criteria funnel. Structural integrity is irrelevant if a site cannot survive the first major filter, regulatory and financial screening. Zoning rules strictly enforce the building's footprint, maximum allowable height, and required vacant spaces. The constraints start with the project sponsor, the entity funding the operation. They define the core purpose of the building and set the strict budgetary limits for land acquisition and development. To navigate these initial filters, sponsors rely on legal advisors and real estate professionals. They assess land use laws, negotiate lease agreements, and ensure the local zoning actually permits the intended commercial or residential use. Legal and financial constraints act as an absolute binary threshold. If a site violates local zoning or exceeds the budget, it is abandoned immediately. This legal filtering saves millions of dollars in unnecessary physical testing. Looking back at the analysis board, the focus shifts to the ground itself. The earth has to physically support the mass of the intended structure. The ideal site sits on an elevated plain with uniform slopes, ensuring rapid, natural drainage of rainwater. Beneath the surface, the soil mechanics must be evaluated. The geotechnical composition has to provide enough bearing capacity to support an economical foundation without the risk of shifting or settling. The most satisfactory construction happens on dense soil or solid rock, usually found beneath 60 to 120 centimeters of light topsoil. High-risk materials like reclaimed earth, waterlogged zones, or expansive black cotton soil react poorly to moisture and pressure. Civil and geotechnical engineers are deployed to extract core samples and prove the ground's mechanical viability. The composition of the dirt dictates the cost of the foundation. Requiring deep concrete pilings to bypass unstable soil can instantly bankrupt an otherwise legally sound project. This 3D diagram tracks the atmospheric forces acting on the structure. These yellow arches map the extreme summer and winter sun paths over the site, which is critical for predicting thermal loads and calculating the building's overall energy efficiency. Simultaneously, engineers map prevailing wind directions. This data dictates passive cooling strategies and alerts structural engineers to specific aerodynamic loads the building will have to withstand. But the environment also contains invisible external threats. This radial map measures noise pollution from a nearby metro line. Environmental consultants overlay these red concentric spheres to gauge acoustic impact and design precise mitigation strategies, like heavy architectural soundproofing. Mapping these invisible forces prevents a structurally sound building from becoming an unlivable oven or an acoustic nightmare. A site is an active node within a much larger urban network. No building can function in a vacuum. Reviewing the utility services block here, planners verify immediate, hard pipe access to the municipal water supply, gas mains, high-tension electricity grids, and sanitary drainage systems. Beyond hard utilities, the site requires social layer analysis. It has to be compatible with the demographic character of the neighborhood and offer proximity to vital amenities like schools, hospitals, and public transportation lines. Ignoring this social layer introduces immense risk. Community stakeholders, local residents, and advocacy groups wield immense power. If a development introduces unmanaged traffic congestion, noise, or negative visual impacts, these groups can delay approvals or destroy the project entirely. This phase identifies absolute failure conditions. Areas prone to heavy river floods, saturated with toxic industrial runoff, or locked in permanent traffic gridlock must be abandoned, regardless of how cheap the land is. Without robust external utilities and strict alignment with the community, a technically perfect building becomes an isolated, unmarketable island. The final step of site selection is data compression. This column on the right takes thousands of raw variables and forces them into a highly actionable SWOT matrix. We can see the synthesis clearly. Wide road connectivity is categorized as a structural strength. The greenery surrounding the plot presents an opportunity for landscaping. However, the extreme proximity to the metro line is firmly classified as a threat due to the noise pollution. This rigorous spatial accounting allows executives to weigh fatal flaws against unique geographical advantages in a single glance. Executing this multi-layered analysis secures an optimal location that maximizes competitive advantage, ensures long-term sustainability, and protects the sponsor's initial investment. Every filter we have examined, from soil mechanics to zoning, serves the same primary objective: preemptive risk mitigation. A hastily selected plot guarantees cost overruns, legal halts, and foundation failures. A project guided by a rigorous spatial model progresses predictably, efficiently, and safely. The final timeline, quality, and cost of a structure are not determined during construction. They are decided long before the first shovel hits the earth.